just a short introduction. I'm very happy that you are presenting today, Hans, and you're a data scientist engineer from Vine Oil and Gas, and we are on time, so I think I'll just leave the presentation to you and look forward to hearing from you right away.
Awesome, thank you so much. Well, thanks everybody for tuning in today. My name is Hasbil Yadi, and today I'm going to talk about some of the applications of some of the machine learning applications in the oil and gas using Python. So before getting started, I'm going to start off with like some basic concepts, and then I'm going to dive into the workflow and finally a case study in Haynesville. But first off, I'd just like to spend maybe 30 seconds defining terminologies here. So what is artificial intelligence? So AI is basically using machine intelligence as opposed to using human intelligence. And then machine learning is considered to be a subset of AI, as you can see from this slide here. And so basically in machine learning, we're giving the computers the ability to learn without being explicitly programmed, which is pretty powerful. So basically training somebody how to play basketball, that is considered machine learning, right? So machine learning is not the same as AI, is a subset of AI, and basically using the computer's ability to learn without explicitly programming. And then deep learning, finally, that you hear a lot about, like a lot of companies use, especially in the tech industry, is a subset of machine learning. So deep learning is a subset of machine learning. And basically in deep learning, we use an artificial neural network with multiple layers. And examples of deep learning are, like, for example, the convolutional neural network, which are used for different purposes, like especially in the oil and gas industry, such as seismic interpretation. We also have the recurrent neural network, RNNs. These are used for time series forecasting, which has a lot of applications actually in the oil and gas industry, especially using the long short-term memory, like LSTM models. So today, I want to hone in on machine learning itself. I want to talk about like a practical workflow to use different machine learning algorithms to find patterns and insight from the data. So my topic today will focus on machine learning. So before getting more into the workflow, I want to talk about different machine learning types. I'm sure you guys are aware that we have supervised, we have unsupervised, and we have semi-supervised and reinforcement learning. So in supervised machine learning, we're talking about having a data set that is labeled or has an output associated with that data set. So if you have a bunch of input features and you're trying to correlate those input features to an output, to one single output or multiple outputs, in which your data is labeled, it is called supervised, which I think we've seen some examples in today's workshop. The unsupervised is basically trying to cluster data. If you have a large data set and you're trying to cluster the data into different clusters, you can use different unsupervised techniques such as k-means clustering and the hierarchical clustering and so on and so forth. And then sometimes you can use unsupervised to cluster the data and then use the output of the unsupervised model, the output of the unsupervised model as the output of your supervised model, and basically call that a semi-supervised. So you basically cluster the data, and let's just say you cluster the data into 3 clusters, cluster 1, 2, and 3, and then you use that output column as the or that clustering column as the output into your supervised model, which is called the semi-supervised. And reinforcement learning, which is to be honest, in the oil and gas industry, I haven't seen many publications on reinforcement. It's pretty new in the oil and gas, but I think it has a lot of it could have some applications in the oil and gas. In reinforcement learning, the machine continuously trains itself on a continual basis, and basically This is one of the powerful algorithms behind some of the self-driving cars that we see today. So I think what you could also combine reinforcement learning with deep learning. You can call it deep reinforcement learning. So I think over the next few years, we're going to probably hear more from reinforcement learning. So today I'm going to talk about building supervised machine learning models, and I'll show you a case study on that. So some of the examples on some of the well-known algorithms within supervised, ANN is probably, you guys have probably all heard of that before. We have support vector machine, we have k-nearest neighbor, random forest, all kinds of decision tree algorithm or tree-based algorithms. We have gradient boosting, we have adaptive gradient boosting. Each one of these algorithms have like certain applications, and depending on the problem that you're trying to solve, some of these algorithms could provide a more accurate result as compared to others. On the unsupervised, as I said, we have k-means clustering is probably used extensively in the oil and gas industry, especially for facies classification that we saw today. The hierarchical clustering is another one. dbScan density-based clustering technique is also pretty powerful, especially if we're not sure how many clusters to choose, you can use dbScan. And on the reinforcement learning side, we have Markov decision process and Q-learning. So today I want to talk about ANN and support vector machine a little bit, and show you a case study how we used these two techniques to drive and kind of get insights from our completions data set. Before going into that, I want to talk about the workflow. So first, the first step in any machine learning model, or before building a machine learning model, is to collect and that data. And as a lot of the presenters mentioned today, a lot of the companies have started to develop data warehouses. So as opposed to just having everything in Excel and having the data in different sources, we can have one central data warehouse. That could be a SQL data warehouse, or or SQL Cloud data warehouse that you can tap into and get that information. So at Vine, we've done a pretty good job. I think we have a SQL data warehouse, on-prem SQL data warehouse that stores pretty much everything that we have, from drilling, from geology to drilling to completions to reservoir to production. We have it all in our SQL data warehouse, and we can pull data easily and basically pull the data into a visualization dashboard such as Spotfire and visualize it. And then, so this is step number one. Step number two is cleaning that data. So spending some time to understanding what's behind the data and cleaning that data is very important, especially if you have some anomalous points, you have points that are considered erroneous and are inaccurate. We pretty much have to remove those points or evaluate the validity of those points prior to proceeding to the next step. So collecting, then cleaning that data, and then one of the steps in data cleaning is data visualization. So you can see here that in the first few steps, we have to visualize the data. So by visualizing the data, I'm talking about just showing, using various Python libraries for data visualization, for anomaly detection. For example, if I'm evaluating a completions data set, if I have a point that says, you've pumped 10,000 pounds per foot of proppant, is that accurate? Well, probably not accurate, right? So we need to remove that or question the validity of that point prior to moving to the next step. So simple plots like distribution plots or box plots, or just simply scatter plots, using the Seaborn library, can really identify a lot of these anomalous points that we could potentially remove prior to proceeding to the next step. Another important step is collinearity removal. I'll show you guys an example. It's pretty important to remove parameters that are collinear. They provide the same information. For example, in the completions world, at the sand per foot and water per foot, usually the more sand per foot you pump, you also pump more water per foot. So if you plot those two parameters, on a scatter plot, you can see a high collinearity. So when the Pearson correlation coefficient or even Spearman correlation coefficient is high, usually more than 90%, you can remove one, because including both into your model could just confuse your model even more. So it is important to remove those collinear features. And then feature ranking and selection, I think we've had some conversations on that today. That's a pretty important piece where you use different types of tree-based algorithms. You can use you can use decision trees, random forest, gradient boosting, extra trees. You can use I would say like 6-7 different techniques that you can use to do feature ranking on your parameters. So feature ranking is the next important thing that we got to do to understand which features have the highest impact on the output of the model. So the features that fall at the bottom of the tree, which I'll show you in a minute, those features can be removed from your analysis and not included because you don't need them anymore. And then prior to actually going into applying machine learning, like one important step, especially if you're using some of the algorithms such as artificial neural network or support vector machine, when using those algorithms, it is pretty important to normalize a data set. And by normalization, I'm talking about taking each input feature and subtracting the min, dividing it by the max minus the min, and that's feature normalization. Or some other algorithms, such as tree-based algorithms, such as random forest, extra trees, do not require neither normalization nor standardization. And some others, such as unsupervised learning algorithms, k-means clustering, those are recommended to use standardization as opposed to normalization, in which you take each input feature, you subtract out the mean, and then divide it by standard deviation. So going back to the workflow section, so we talked about collecting data, cleaning data, and then normalizing or standardizing the data, right? So now, once you have all that information ready to go, the next step is to find out what type of model to use. And the type of model to use is really a function of what kind of problem you're trying to solve, how much data you have. And in those cases, you can try different models to see which one provides the highest accuracy. So in this case, we'll do a cross-validation. And cross-validation is just a process of splitting your data into a training and testing set. So let's just say you feed in your model, 70% of the data is fed into your model as training, and then you train the model based on 70% of the data, and then you test it on the remaining 30% of the data to see how your model performs. And if that's good, you can also do one final validation, which is called blind set validation. And in that case, you just simply feed in the model a data set that has never been seen before and see how it performs in that blind data set. And then if it does well in the blind data set, then you are pretty much in a good shape to go, and you can go to the next state, the next phase, which is deploying the model. So these are some of the applications in the oil and gas. You have completions and wall spacing optimization. You have type curve clustering using unsupervised learning techniques. Rate of penetration drilling optimization is pretty powerful. You can use different machine learning models to optimize the rate of penetration during drilling. And you can actually couple that with other optimization algorithms such as genetic algorithm and particle swarm optimization to really find the best parameters that maximizes your ROP. And then number 4 is predictive maintenance. You probably hear a lot about those. Liquid loading detection. This is another powerful technique to use unsupervised learning methodologies to find when a well is loaded and actually deploy that model real time to help you make real-time decisions. And we're talking about deploying these models on an edge device so you can make real-time decision to create value for a lot of the companies. Plunger lift and imminent optimization. This is another powerful technique, or is another powerful project that you can use machine learning on. Fall detection through seismic data, geomechanical log prediction. These are pretty simple ones actually, like geomechanical log prediction, especially predicting shear and compression wave travel times, and using those to calculate Poisson's ratio, Young's modulus, closure pressure, and so on and so forth. So these are actually pretty, powerful ways of really being able to predict logs in areas that you don't have. And then facies classification, I think people talked about that. And then frac chemical optimization is another area that has a lot of potential, petrophysical and geomechanical properties, and then surface treating pressure prediction using deep learning, in this case, long short-term memory. So these are some of the applications, some of the Python libraries that I've used for this project here, and are pretty well known. NumPy is a fundamental package for scientific computing in Python. It's basically the linear algebra library, like in Python. Pandas, you guys have all heard of that before, is built on top of NumPy, and people regard Pandas as the Python's version of Excel. So Matplotlib is very popular visualization library in Python. You can really do all kinds of plots in Matplotlib. It's not as nice looking as Seaborn, but it gives you a lot more flexibility in terms of adjusting your figures, as opposed to Seaborn, which is very powerful. It's actually one of my favorite libraries, but you have some limitations with Seaborn. And then some of the platforms that I saw today, it looks like they were built on top of Plotly. So Plotly is actually interactive, it's an open source interactive visualization library, very powerful, highly recommended, and actually coupling Plotly with Dash, you can create dashboards, using just Plotly and Dash. If you don't want to use Spotfire or Power BI and just want to, create your own kind of dashboards, you can couple Plotly and Dash, and basically the combination of two are pretty powerful tools to create very nice interactive dashboards. And then scikit-learn is basically like, as you guys know, is a machine learning library used for all kinds of problem solving, such as classification, regression, and clustering problems. And also pretty much all of these, a lot of the algorithms that I showed you in like a few slides ago, those are all can be found within scikit-learn. So building a machine learning model with scikit-learn is fairly simple and straightforward, and they've done a pretty good job updating those libraries and really keeping up with the latest and greatest technologies. And TensorFlow is, you guys, I think we've had some talks about those. This is also a powerful deep learning library that you can use for using, like for example, the CNN or solving problems such as the using LSTM to predict the frac treating pressure, gas pricing, and other problems. So this is like an example. So these are from a Haynesville case study. We have a bunch of input features on the left hand side. You have a hidden layer, one hidden layer in the middle, and you have an output. So we're trying to basically understand the relationship between cluster spacing, stage spacing, sand per foot, sand to water ratio, average treating rate, and so many of those geologic features to the productivity, which in this case we're defining the productivity as EUR per 1,000 feet. So we built two different models. We built an ANN model, and also we built a support vector machine model to understand what is the impact of each feature on the production performance, which is in this case defined as EUR per 1,000 feet. So this is actually a pretty simple model. We can actually be more creative with this and say, okay, instead of one output, we can have multiple outputs. We can have, cum 30 per foot, cum 60 per foot, cum 90, all the way to cum 2 years per foot. That would actually be a multi-output machine learning model then. But in this case, this is a basic model that we built, trying to understand the relationship between all the input features and output feature. And ANN is actually pretty straightforward. Like the basic fundamentals of ANN is that you have an input, you multiply it by the weights of these neurons, and then you apply an activation function, then you add a bias, then you get your output. And basically, like what you do in this case is once you get your output, the objective in an ANN model is to minimize a loss function, and that loss function is simply defined as the difference between your predicted value minus your actual value. So for example, if on the first iteration, my EUR per 1,000 feet turns out to be 2 BCF per 1,000 feet, and the actual was 1.5, what the model does, it goes back, it back propagates into this hidden layer, and it changes the weights of these neurons, and basically updates those weights and runs it again, and basically now you have a new EUR per 1,000 feet. Let's just say it's EUR per 1,000 feet is now 1.8 BCF, and the actual is still 1.5. It keeps iterating through those epochs until that objective function of minimizing the loss function is converged or reached. So that's how a basic neural network works. It's pretty actually simple, but it's very powerful, especially as you get a lot more data. So in the past, one of the biggest breakthroughs in AI has been in deep learning, and the reason for that is because you have the amount of data has increased tremendously. You have GPU capabilities now. You have graphics user processing now, and also you have toolboxes such as TensorFlow. You can deploy these models pretty rapidly. So what we've seen, I think in the past 10 or 20 years, the biggest breakthrough in AI has been deep learning, and because in the past, you did not used to get good results, but now with the amounts of data that has increased tremendously, you have a lot of potential from just deep learning itself. Now, I talked about the collinearity removal. This is just simply showing you all the parameters, cluster spacing, stage spacing versus the other parameters. So this is used to find features that had high collinearity, that have a high Pearson correlation coefficient. And Pearson correlation coefficient is defined as the covariance of x and y divided by the standard deviation of x times standard deviation of y. So as I said, in this case, we removed stage spacing, and we also removed water per foot, because stage spacing was heavily collinear with cluster spacing, and water per foot was heavily collinear with sand per foot. So we removed those two features, and we used the rest of the features and basically built a proceeded to the next step. So this is just a simple one line of code using the Seaborn library sns.heatmap to kind of provide you this heat map of what is the relationship between different features in order to be able to remove collinear features. Next is feature selection, feature ranking, model selection, and grid search. So we use, as I said, there are different algorithms that you can use for feature ranking. Some of the most well-known algorithms that a lot of data scientists use are called random forest. You can use extra trees. You can use gradient boosting. You can use CAD boosting. There are all of those algorithms should give you similar ranking. They're not going to be the same. They're not going to have the same exact coefficients, but they should give you some type of a feature ranking to kind of for you to identify which features fall at the top of the tree and which features fall at the bottom of the tree. So random forest is a powerful one. It's basically a combination of it's an ensemble of decision trees, as opposed to using one decision tree. You can use thousands. You can actually specify how many trees you can use, in your model, the number of trees within the scikit-learn. So by defining more trees to use, it usually helps you with being more accurate on your prediction. So random forest is pretty popular. So we use random forest to understand what is the importance of each of these completions features on the output feature, which if you recall, it was EUR per 1,000 feet. As you can see here, you have sand per foot and cluster spacing falling at the top of the tree, followed by sand to water ratio and some of the geologic features. So this is, again, it is in a particular area in Haynesville. This is not the case in the entire Haynesville, or this is just one subsample of a large data set that I picked for this case study. but it gives you a lot of indication as far as what parameters to hone in on. It tells you that you got to hone in on SAM per foot, you got to hone in on cluster spacing, and some of these important features. So next, support vector machine. So I'm almost done. So I'm just going to go through what support vector machine is and then go through some of the results. So in support vector machine, basically what we're doing is we're trying to maximize the margin between these support vectors. So as you can see here, you have a classification problem here. You have the red dots and the green dots. And the idea is to maximize the margin through a separating hyperplane. So we're trying to draw this hyperplane, this black hyperplane, in a manner that would maximize the distance from these closest circles, green and red circles, to this. So if I drew this way, it probably would not maximize it on both sides. It would probably maximize it on one side. So we're trying to draw it in a manner that would maximize the distance between these support vectors to this black hyperplane. And it's actually a pretty powerful algorithm that you can use. It is basically one of the machine learning algorithms that we discussed. It is a supervised learning algorithm as well. And if I go to the next slide, we talked about the ANN, and the objective was to minimize this cost function here, which we talked about, the input layer, the hidden layer, and the output layer, and the concept behind back propagation, when you back propagate back to the hidden layer and basically change the like neurons and then go through those iterations. And then grid search is basically used to find the optimum hyperparameters. So in grid search, it is ideal to each machine learning model, like for example, the ANN model, you can define what type of solvers to use. You can define what kind of activation function to use. You have to define what kind of, how many neurons to use, how many layers to use, right? So it can be pretty tedious to find the best hyperparameters within an ANN model or within any machine learning model. So that's why it is important to use grid search to run. It's basically a nested for loop that basically finds you the best hyperparameters that would result in the highest accuracy. So one of the disadvantages of grid search is that it takes a long time to run. So you can, if you have a large data set, it might take you days, if not weeks, like for your computer to constantly run to find the best hyper tuning, like the best hyperparameters. But it is pretty important to make sure the machine learning model that you build is a general machine learning model. You can apply it to a blind set and it does a good job. And grid search helps you finding the best hyperparameters for your model to make sure your model does not fail when it goes to production. So now I talked about all of this. You might say, Haas, what's the point of all of this? This is all a lot of theoretical stuff. Show me some value. Okay, so now you build a model. Now you can predict what is the impact of each parameter, of each of your completions parameters in this case, on your production output, and find out. You can then run economic analysis. You can do all kinds of stuff with it, right? This is called a one variable at a time sensitivity, or called OVAT. Okay, and OVAT, and I use the support vector machine model. I also use the ANN model. The results are very similar after fine-tuning the hyperparameters. This basically shows what is the impact of increasing my cluster spacing on my EUR per 1,000 feet. Again, I removed the numbers just for this, in this case, for confidentiality. But you can see here that as you increase your cluster spacing, your EUR per 1,000 feet goes down. But if you see here, going from here to here, the difference is not really much. So you can then run your economic analysis to see how much really, which cluster spacing is actually the optimum cluster spacing, as opposed to just choosing the lowest cluster spacing in this case. This is the number of clusters per stage. You can see it looks like right around here, you have the optimum number of clusters per stage. This is SAM per foot. There is no breakover that was observed on a SAM per foot. So this is also pretty important to know that as you increase the amount of sand that you pump during hydraulic frac jobs in this particular field, you're also increasing production. The sand to water ratio shows that as you increase the number of, or the amount of sand to water ratio, which essentially means you're pumping more sand in relation to water, you're decreasing production performance, which means that you need to pump more water in relation to your sand in this case. And then finally, rate is the impact of rate on your EUR per 1,000 feet. And basically, that's all I've got. I just wanted to show you a case study, go through the workflow. But that's all I've got. I'll take any questions. Feel free to connect with me on LinkedIn. I also have an Observer Intelligence podcast where I invite various guests, talk about AI and machine learning. Usually a lot of different professors from different universities, and basically pick their brain on the impact of AI. So check out the YouTube channel, Observer Intelligence. And finally, we have a book coming out called Machine Learning Guide for Oil and Gas Using Python that will be released on April 1st, which is currently listed as Amazon's #1 release in petroleum engineering.
Thank you very much for your presentation. This was very interesting listening to. Are there any questions? Feel free to, as pointed out, feel free to direct them through email or LinkedIn, whatever, or